So let's talk about the photoelectric effect today. The photoelectric effect is a fairly famous phenomenon in the world of physics, and I think today we want to talk about just a little bit about how it works and one interesting application of the effect. What is this effect? So the photoelectric effect is the emission of electrons when light of the right frequency hits a metal, and typically a metal anyway. The effect was first discovered in 1887 by two scientists, Hertz and Hallwachs. However, it really wasn't until Albert Einstein studied the phenomenon that we really had a good answer as to why it takes place. And so I've got on the screen for you a diagram of various light sources hitting a photoelectric material. And we'll come back to that diagram, what's going on there a little later. So first I want to talk about a little bit of the history behind the effect. So you may or may not know that earlier in like the 18th century, for example, physicists thought of electromagnetic radiation as a wave, and just as a wave, not as, today we have the wave-particle duality, but at the time it was just a wave. And the photoelectric effect was really what cemented the idea of that wave-particle duality, that the fact that electromagnetic radiation can be either a wave or a particle. And in fact, so we were talking about Albert Einstein earlier. He actually explained this effect by rejecting that common notion that light was a wave. So the way he explained this effect was using the fact that light came in discrete bits, which he called photons. So that is it was a new-ish idea. It wasn't actually like just blowing people out of the water, because there was a guy before him, Max Planck, who had thought of this idea before. So Albert Einstein actually piggybacked a little bit off the work of Max Planck, Max Planck's publications on blackbody radiation. So this idea of quantized light really was Max Planck's idea, and Albert Einstein used it to help explain the effect. But the two men did help propel the world, into the quantum revolution. So you can see in the picture there, Max is not looking too happy that it was his idea, but Einstein ended up getting the credit for this one, although Planck was obviously very famous himself. So let's take a little more in-depth look at what's going on with this effect. Okay, so I've got some crudely drawn, photoelectric material with 3 electrons there. Okay, so remember that the photoelectric effect is the idea that light can cause some of these electrons to eject and be released. But remember that electrons are bounded to their nucleus, right? They're not just flowing around. They are actually bound to the nucleus. So it's going to take a little bit of energy to get the electrons to be emitted to break, kind of the bond it has with the nucleus. So let's go back to the diagram we had on the first slide. So we see we have 3 different wavelengths of light, 3 different colors of light, and the red light does not have enough energy to break those bonds that the electrons have at their nucleus, right? It doesn't have enough energy to emit the electrons. And the green light, which is a different wavelength, different frequency, seems like it does, because we can see that there are electrons being emitted with the green light. And it's kind of curious that the blue light, which you can see has the smaller wavelength, the higher frequency, it's emitting the electrons, and it looks like those electrons are actually being emitted more quickly than the green case. And just a terminology note, those emitted electrons, we typically refer to those as photoelectrons when they're ejected due to the photoelectric effect. So I think that's kind of curious. Why does this diagram depict the blue light emitting the electrons quote unquote faster than the green? We can actually analyze the situation using no more than high school physics. And if you've ever taken a high school physics course, you know that like 90% of the course is just conservation of energy, right? I mean, that is, you hear that a million times. So we're going to actually talk about this effect in terms of conservation of energy. And what you may remember is that the conservation of energy is just that in a closed system that the total amount of energy does not change. There's a set amount of energy in a closed system, and you can transition between different types of energy, but you're not going to change the total amount of energy. So let's analyze this problem by just looking at the interaction. So first we have the photon coming in, and for the sake of simplicity, let's just look at one photon with interacting with one electron. So Einstein says that photons have the energy E is equal to hf, where h is Planck's constant. It's just a fundamental constant in the universe, and f is the frequency of the photon. When the photon hits the plate, it is absorbed, and then an electron is released. Now, electrons have mass, so this released photoelectron will have kinetic energy since it's moving and it has mass. Thus, the energy that was in the photon must have been transferred to the energy of the electron. Well, kind of. Don't forget, some of the energy of the photon went into breaking the electron free, right? Because it's bounded to the nucleus originally. It takes energy to break it free. So the energy in the final state of the system is that energy that's required to break the electron free, that photoelectron, and let's call that E sub naught, and the resulting kinetic energy of the photoelectron. So we have an expression that looks something like that. Now, due to conservation of energy, we can actually equate these two expressions, and that gives us a nice mathematical representation of the photoelectric effect, and there it is. You can see it on the screen. So notice that that Planck's constant, h, and E sub naught are both constants. Thus, once we have enough energy to actually break an electron free and get a photoelectron, from that point, an increase in the frequency of light will cause an increase in the kinetic energy of the photoelectron. So that's why you kind of see in the diagram the higher frequency light depicted the photoelectrons as having a higher kinetic energy. So the question is, right, how do we know if the photoelectric effect is going to occur or not? Like, I've got this material, I've got some light. How can I predict if I'm actually going to get an effect? And it's actually a pretty simple thing to calculate. So let's borrow some equations from the last slide. So we know that the energy of an incoming photon is equal to E sub naught, some constant that depends on a particular substance, plus the kinetic energy of the photoelectron. Okay. This is to say that we can write the kinetic energy of the photoelectron like that. Okay, so we just did a little bit of algebra there. Now it's important to know that E sub naught can actually be written in a different way. It can be written as some threshold frequency times Planck's constant. Okay, so you can actually write E sub naught in that alternate form. So let's do a little substitution. Okay, so all I did was substitute h times f sub naught for E sub naught. And then I factored out Planck's constant. And I just realized there is a notation error. That should not say h sub naught in the middle. That should say f sub naught. So here's my notational error. That should say f sub naught. And that should just be h. That's just Planck's constant. Okay, so I just did a little factorization there. But we're talking about kinetic energy here. So you can't have a negative kinetic energy. So if this expression is going to make sense, there's a pretty obvious stipulation on the relationship between F and F sub naught. That is to say, F has to be bigger than F sub naught. So for a given material, remember that F sub naught is just a constant that is unique to a given material. Okay, so if we want the photoelectric effect to occur, we just need that the frequency of the light that we shine on this material is greater than that's what's called that threshold frequency. That's what that F sub naught stands for, that threshold frequency of the given material. So the big question is, so what, right? What's the deal with the photoelectric effect? Who cares? Why is this an important effect? And there actually are many applications for this, and a lot of them are even useful. So there's imaging technology, CAT scans. You can actually do a chemical analysis of certain elements in their nuclei. I don't want to talk about that. I'm talking about the coolest application, which has to be night vision goggles. And I love that GIF right there. So my inner child tells me that this is probably the coolest effect, or the coolest application of the photoelectric effect. So let's give a quick rundown of how night vision goggles actually work. How are they using science? How are they using the photoelectric effect to give us these really cool green images? So it turns out they're very complicated. So night vision goggles are about as complicated as they are awesome. We're going to summarize it and be very brief, but give you a general outline of how this works. So basically what happens is the photoelectric effect is used to amplify the presence of individual photons, because obviously in a low light environment there's not a lot of photons floating around. So we need to make the most of the ones that we can pick up. So what happens is the lenses collect photons and channel them to a material with a coating of photoelectric material. The photoelectrons are then accelerated through a large potential difference, and so we should probably be looking at maybe the left-hand diagram right now. They get funneled through this potential difference to what's called a channel plate, which is just a plate full of fine holes. Okay, so in this diagram you can actually see the incoming photons right there falling through a hole, which the diagram calls window. So when the photoelectron strikes a hole, it ionizes atoms at that point of impact, and which results in even more photoelectrons. And that process is just repeated, and every time we have an impact, there's more and more photoelectrons released. Okay, and you can kind of see that in diagram as they kind of repeat that process. There's more and more photoelectrons. So we call that part of the device the photomultiplier. So it takes, and in fact, you could take one photon coming in and you can get several thousand photoelectrons leave. So it really does a great job of taking a little bit and turning it into a lot. Okay, so once you have all these electrons, they're accelerated and hit a screen, and then an image is formed. Okay, so you can now we can look at that right-hand diagram. Once you get out of that section number 3, which is yellow, it says photomultiplier, it gets hit to a screen, and then of course those electrons form an image on your screen, and then you get a fairly distinct image where, usually in a low light environment you wouldn't be able to. So it was always kind of cool to me to think that for those of you who are Step Brothers fans, Albert Einstein had a minor indirect role in the making of Step Brothers. And that to me is perhaps not the most useful, maybe not the most world-changing application of the photoelectric effect, but to me it's the coolest, so that's the one I wanted to talk about.